Hey there and welcome. I want to extend a really warm greeting to all the brothers out there on the plant floor today. Look, if you're a wastewater operator or a WWTP manager, you already know that our jobs require constant, around-the-clock vigilance. So today, I'm bringing you a highly practical explainer covering a step-by-step standard operating procedure for literally one of the most stubborn issues we ever have to face: persistent foam in our aeration tanks and secondary clarifiers. I know exactly how stressful it is when a plant just starts foaming over, so we're going to walk through exactly what you need to do to get things under control. Step by step, nice and slow.
So here's our quick roadmap for today. We'll start with the foaming problem itself, move into identifying different foam types, investigate the root causes, lay out specific scenario action plans, and finally, wrap up with an emergency checklist.
All right, Section 1, the foaming problem and its impact on WWTP operations.
You know the exact site. When this persistent foam gets to be, say, 10 to 50 centimeters thick, it just completely disrupts our operations. If it spreads across more than 30 to 50% of the surface area, it's severely limiting the oxygen transfer in that surface zone. And worse, it can overflow the railings, creating this massive sticky mess that eventually dries out and just hardens like cement on the concrete and equipment.
Man, I know how tough it is for you brothers out there dealing with this, especially on a cold or rainy night shift. First and foremost, when that foam overflows the walkways, it creates severe slipping hazards for you and your whole team. Safety first, right? On top of that, dense foam creates these localized anaerobic zones that release extreme H2S and mercaptan odors. We also end up facing brutal total suspended solids, or TSS, spikes in our effluent. Why? Because the foam literally traps the biomass and carries it right over the clarifier weirs. There are even severe fire risks if hydrocarbon vapors get trapped inside those bubbles. And of course, there are the inevitable community complaints when that smell hits the neighborhood.
Moving on to Section 2, identifying foam types through visual diagnosis.
Take a mental screenshot of this breakdown right here, brothers. Matching the exact color and texture of the foam tells you exactly what you're fighting. If it's a light, fluffy white lather that breaks apart pretty easily, well, you're likely dealing with surfactants, high proteins, or just some young sludge. But if it's a stiff, chocolate brown or gray paste, the kind that won't even break when you blast it with a high-pressure water hose, you're almost certainly fighting filamentous bacteria like Nocardia or Microthrix parvicella. Now, black, foul-smelling foam, that points straight to anaerobic decay inside those thick foam mats. And if you're seeing tiny, persistent white pin foam in your effluent, that usually means you've got excess surfactants or polymers floating around in the system.
Whether it's that stiff chocolate gray paste overflowing the tanks or just a light, fluffy white lather, identifying it early absolutely saves the entire facility from going out of compliance. Think about it. If you misdiagnose the foam, you might end up applying an anti-foaming agent that only masks the symptom, all while the biological health of your activated sludge is quietly deteriorating underneath.
All right, Section 3, root cause investigation and tracing the problem to its source.
So, we need to get off the walkways, get into the lab, and run some critical tests. If you suspect chemical cleaners are the culprit, you've got to run an MBAS analysis to check for active surfactants in the influent. You also need to verify your dissolved oxygen and your MLSS levels. For example, if your MLSS is dropping below 1,000 milligrams per liter, yeah, you're more than likely dealing with young sludge.
Now, to truly confirm a filamentous issue, you must evaluate the Nocardia count index under the microscope, grading it on a scale of 0 to 6. What you're looking for are gram-positive, branching filaments. If you look under the lens and see what looks like a crazy tangled web, you know exactly why that thick brown foam is plaguing your aeration tanks.
Let's pull this into a concrete protocol. This builds into a really reliable 5-step root cause investigation that you should run every single shift. Step 1, visual observation of the color and texture. Step 2, get that sludge under the microscope for a Nocardia count. Step 3, run your MBAs and protein analysis on the influent. Step 4, check your sludge retention time, or SRT, and your localized DO levels. And Step 5, trace things back into the factory to see if there are any new clean-in-place, or CIP, chemical discharges hitting your plant.
Okay, Section 4, Scenario Action Plans and Emergency Protocols. Let's get into the fixes.
First up is Scenario A. This happens when we're dealing with that super stubborn, stiff brown foam caused by filamentous bacteria like Nocardia. This foam is incredibly stable, guys, and it's not going to go down without a fight.
So in the first 0 to 2 hours, you need to hit it hard with continuous surface water sprays to push the foam into a collection corner and then use vacuum skimmers to physically yank it out. You can use a silicone-based anti-foam here, but keep the dose minimal. You really don't want to mask the underlying issue or accidentally drop your dissolved oxygen. Then, over the next 2 to 24 hours, aggressively flood waste your sludge to push your SRT way down to between 3 and 8 days. Narcardia grows pretty slowly, right? So basically, washing them out is your absolute best short-term weapon. Also, be sure to keep your influent fats and oils below that 15 to 20 milligrams per liter mark.
Next is scenario B. This one is usually signaled by that light, easily breakable white foam that suddenly flares up right after an industrial cleaning cycle.
When this stuff hits, immediately cut or buffer the incoming chemical flow in your equalization tank so you don't send a shock load straight to your bugs. Activate those surface sprays. Then, over the next 24 hours, you've got to work directly with the production side of the facility. You need them to either lower the detergent concentrations in their CIP program or pump up their intermediate rinse cycles. If the surfactant concentration is just way too high, you might even need to pre-treat that incoming flow using coagulation and flocculation.
Moving right along to scenario C. This is what happens when we get hit by high-protein loads. We see this all the time in food, beverage, brewery, or slaughterhouse processing plants. First things first, contain the spill quickly by dialing up your skimming frequency. Run out to the factory and check for abnormal dumps, maybe a ruptured tank or a massive post-production equipment wash just happened. Then, you need to correct your food to microorganism ratio, bringing it back to a nice, healthy 0.2 to 0.5 range. Crucially, make sure your nitrogen and phosphorus nutrients are perfectly balanced, because if your bugs get starved of nutrients during a high organic load, they're going to excrete these slimy polysaccharides that trap bubbles and just make the foaming so much worse.
Finally, we have scenario D. This occurs when we experience a massive cod shock that results in this white, fluffy, young sludge foam. It basically happens when the bacteria are just growing way too rapidly and haven't formed dense, mature flocks yet.
So the crucial point here is to restrict that incoming high COD flow immediately at the equalization tank. Do not let it drown your biology. Over the next day, if your sludge is too young, you might actually need to import seed sludge from another healthy system just to get your MLSS safely back up over 1,500 milligrams per liter. And hey, always make sure you're double-checking that any anti-foam you're using is actually the correct chemical type for your specific plant.
Almost done. Section 5. The emergency checklist and shift leader protocols.
Honestly, print this list out, laminate it, and stick it right there on the wall in the control room. Running through these 9 checks systematically guarantees you are actively managing the crisis, not just reacting to it in a panic. Let's run through it. Check the color. Check your MLSS. Look under the microscope. Verify the CIP schedule. Calculate your SRT. Read your DO levels at the selector zone. Ensure your skimming is active. Check the water spray pressure. And finally, communicate with the production team. Follow these exact steps, and you will absolutely stay in control of the plant. But brothers, I want you to always remember this golden rule of wastewater engineering. Maintaining proper alternating anaerobic and aerobic zones, your selector basins, is your absolute best long-term shield. A properly designed selector gives your good flock-forming bacteria a massive competitive advantage, so those nasty nocardia filaments never even have a chance to dominate the tank in the first place. I want to leave you with this final, provocative thought. Will an accurate nocardia count today actually prevent your next major foam over tomorrow? You bet it will. Stay proactive out there. Keep your microscopes dialed in and calibrated. Keep those communication lines with the factory floor wide open, and ask yourself at the end of every single shift, have I done absolutely everything today to keep this plant running smoothly tomorrow? Thank you for all your hard work out there, brothers. Stay safe and keep that water clean.